Hello everyone, my name is Ifra Idris. I'm a fourth year PhD candidate at Brown University. My advisor is Dr. Stephanie Telix, and I'm a part of Big AI and Human to Robots Lab. Today, I will be presenting my project where we enabled the robot to aggregate spatial temporal instances of objects for efficient object retrieval over long periods of time. Now, imagine a scenario where we, as humans, we misplace our keys. And we ask ourselves this question as to where did I leave my keys? This requires us to actually look over all the memories that we have in our mind. Home service robots can assist the human users in such a scenario by retrieving spatial temporal information about objects from their long term observations in a partially observable environment.
Now, this is not as easy as it sounds. As we allow the robot to monitor over long periods of time, what it's going to get as input are all these partial view detections of the object. With the state of the art solutions, the robot will still have to look over all these countless detections in order to answer a simple query such as where are my keys, which is not efficient at all. And as the amount of time that a robot patrols the environment increases, the amount of time that the robot will take to answer such a query will also increase, affecting the human user experience. Now, the existing solutions for object retrieval, they fall into the following three categories. Please note that these solutions still give us the countless partial view detections that the robot needs to search over to answer a simple query. Now, these solutions, they either assume that there is fixed observability, full observability of the environment, or they do handle partial observability, but only handle videos for over seconds of data. Or they're even able to handle partial observability and are able to to search over long periods of data, which spans over hours and days. However, they don't take into account the spatial information of objects in the physical environment, and hence they don't focus on making an efficient and equatable spatial temporal representation of objects in the environment. Now, to solve the challenges which are actually introduced by partial observability in long periods of time, we introduce an algorithm which is D3A. Now, D3A aggregates or condenses partial view detections of unique object instances, and it associates them over time. These aggregations are then stored in a storage efficient and queryable spatial temporal representation. D3A is able to create this spatial temporal representation without knowing the type of queries or the attributes of objects in advance. Further, it is able to handle uncertainty in the object poses that might be present because of uncertainty in the robot poses. Further, it is also able to handle the fact that the object can move out of sight in the environment. Before we delve into the technical approach and quantitative evaluation,
Here is a robot demonstration. Hey Kari, where is the pink cup?
I have found two locations of the pink cup. The keyframes of the two instances along with their spatial temporal information is shown on the computer screen.
Please note that for this demo, the speech recognition and generation was done off the shelf, and the natural language processing of the query was template based. If D3A was not used, these are all the frames that will be returned for the query asked in the robot demo by a naive algorithm that stores all the detections in the database without any spatial temporal association. A human will have to look over all these frames to find the pink cup. While D3A returns only two keyframes, these keyframes and their associated time intervals are overlaid on the map according to their returned locations.
D3A performs detection-based three-level association to identify the keyframe that best represents the unique object instances. Tier 1 D3A performs unsupervised clustering over the object-centric information which is extracted from the raw visual sensory data. Moving forward, in Tier 2 filtering, D3A uses the aggregated clusters, keyframe centroid clusters of the current sliding window to update spatial temporal information of the objects that the robot has seen in the past. This spatial temporal information of the previous objects is stored in the short-term memory. Once the short-term memory buffer gets full, the least recently viewed object by the robot is actually popped out, and it is used to update the entries which are stored in the persistent storage spatial temporal collection represented by capital R. In both Tier 2 filtering across multiple sliding windows and Tier 3 filtering across database entries, our algorithm needs to make a decision whether the aggregated cluster of the object instance is a new object, and hence it should be added as a completely new entry in both short-term memory buffer and in our persistent storage efficient storage as well. Else, this aggregated cluster includes partial view detections of an object instance that has been previously viewed by the robot. In this scenario, those entries in both the short-term memory buffer and in the persistent storage that are closest in cosine similarity of the feature vector and in Euclidean space of the object poses should be updated in tier 2 and tier 3 filtering respectively using the aggregation function. For our evaluation, a weighted average aggregation function is deemed to be effective. Now we go back to our motivation where we want the human to query the storage efficient spatial temporal representation and retrieve the information about the object as efficiently as possible. Now, any template based NLP methods, they can actually be used to map natural language query to the set of object IDs, time intervals, location, and areas. That is to convert it from this natural language to this formal representation. And this formal representation is what D3A actually takes as input for object retrieval. Now, this table actually shows the type of queries used in our evaluation. Now, D3A is not only able to handle queries where specific attributes such as orange bowl, specific spatial relations such as together, or specific temporal information such as between 1 p.m. and 4 p.m. is provided. It can also actually handle the queries which are generic as shown in column 2, and it can also handle negative queries when the object of interest is not present in our aggregated spatial temporal representation. Now, moving on to the evaluation. The aim of our evaluation is to actually test the hypothesis that a database-backed system with our algorithm D3A, it actually improves the compactness of the spatial temporal representation of objects in the environment. As a result of D3A, the size of the spatial temporal representation is way less as compared to the original sensory data. Further, D3A also improves the object retrieval performance when a human queries the spatial temporal representation, and it does so by returning a small subset of keyframes. We measure the object retrieval performance by a number of metrics, such as the total retrieval time, the total evaluation time, but also we measure the mean number of frames that are returned when a human user queries a spatial temporal representation. We also measure or look at the rank of the frame amongst the returned keyframes, which contains the desired correct spatial temporal information of the object of interest. Now, to test our hypothesis, we actually perform a real-world evaluation using both a range of syntactic detectors, which are built from the ground truth data, to actually control the noise level. And we also perform evaluation with real detectors, which are deployed on a mobile robot to actually assess the system's end-to-end accuracy. Now, for data collection, we actually allow our mobile robot Curry to patrol in a robotics lab environment for 4 days. This environment was uncontrolled and it was cluttered in a sense that the people, they were allowed to use the space as this. Now, from this table, which is also shown in our paper, the key takeaways are actually highlighted in the red box. For just 22 hours of data, the amount of data that we collected was 10.5 gigabytes, which was proportional to a large number of things, which is around 10,000, and a large number of detections, which was 13,000. And you can imagine that and this was just for 1 day, and you can imagine that the number, as the amount of data, it increases to being more than 1 day, this is going to linearly increase. And what we did for ground truth annotation, we annotated 3 hours of data, and in that the ground truth objects, they were around 59, out of which 49 was static, and dynamic were just 10 objects. And more details about the CFS are in the paper. And this is the link. The QR code provides a link to the GitHub repo where you can find samples of the type of data that we collected. Now, for this project, we actually performed 4 experiments. However, in the interest of time, I will only be able to provide details about the second experiment. Experiment 2 has been chosen because it most closely correlates to a user study and shows the object retrieval performance as our aggregated spatial temporal representation is queried. In our second experiment, we compared the retrieval performance of D3A against the knife baseline. Now, D3A plus D represents D3A's aggregation method, which include the real detector, detectron, and color histogram. And the naive baseline, it inserts every detection spatial temporal information directly into the database without our aggregation method. Please note that the spatial temporal information that is inserted into the database by the naive algorithm is still we are still able to index it over both space and time. And we experiment over all these three types of queries that I have previously mentioned. Now, query retrieval performance, it depends on multiple factors. The first factor is the type of query that the human asks. The second factor is the aggregation method that we use for making our spatial temporal representation. And the third factor that affects the retrieval performance is actually the query precision. That is, once the human queries the spatial temporal representation, how accurate is the natural language processing? For this, we actually discretize the query matching precision, and the uncertainty, it is categorized into three levels. The first level is the perfect level, where natural language processing is completely perfect and is able to match the object of interest in the natural language query to an exact object ID in the database. While the worst query precision is of any object level, where the NLP is the worst, and it maps the query to the most generic set of all the object IDs in the data. This brings us to the spec table, which is described in detail in our paper, where we measure the total retrieval time, evaluation time, and also measure the mean number of frames and the rank for finding the correct frame for every query type, query precision, and aggregation method. Let's focus on just the query retrieval performance when the query precision is any object, which is the worst query precision. In this case, D3A plus D, it actually returns 54 frames on average, which is as compared to 1,933 frames which are returned by the naive baseline. This difference in the number of frames that are returned, they are also reflected in their retrieval time and evaluation time, which means that when the query precision is the worst, D3A still performs better in terms of human user experience as compared to 1933 frames. Now, if we look at the overall performance for just 3 hours of data, D3A's overall accuracy for finding the correct object of interest frame is 81.98%. And further, D3A plus D only takes 24 milliseconds to retrieve and evaluate the frames for all the object instances, while the baseline actually takes around 1,137 milliseconds. Please note that this is just for 3 hours of data. As the number of hours of data increase, the retrieval and evaluation time for the naive baseline is going to increase linearly since we don't do any aggregation method. And again, another way where we see an improved user experience is the fact that with D3A, the user's query will be answered by searching over a really smaller amount or number of keyframes, which is just 25 as compared to the average number of 788 frames for the naive baseline. However, our system is not perfect. Our system fails to identify all spatial temporal locations of the unique object because of errors in clustering and also because of errors in detection. Our algorithm, by aggregating spatial temporal instances of unique objects, opens up menu for object retrieval and other surveillance-related applications as well. Interesting extensions to our work will be to test D3A in open domain environments and also to conduct a user study evaluation. Currently, we are working on human-robot dialogue and task planning, where the robot senses the states and the locations of objects in the environment and also smart home sensors, and based on this is able to assist the user in completing the activities of daily living. Our focus is again to help the elderly, specifically those that have dementia and might not be able to complete these activities of daily living with the most ease of effort. In conclusion, we present a novel algorithm, D3A, that aggregates partial view detections of unique instances to create a compact and queryable representation of the objects. D3A does so by doing detection-based 3-level association of unique object instances. Through our evaluation, we see that D3A significantly outperforms the baselines in efficiently answering spatial temporal queries over long periods of time. And we measure this object retrieval performance through a lot of metrics, some of which are the retrieval and evaluation time and the mean number of frames that are returned. A robot deployed with our algorithm D3A was able to process 22 hours of sensory data into a compact and queryable representation. This is an encouraging step towards enhancing the sensory capabilities of home service robots that can help the elderly in finding their lost and forgotten objects. Thank you so much for taking out time to listen to my presentation. I'll be more than happy to answer any questions during the Q&A session. Thank you.